Okay, so let's move to the case 3. Is unlimited source, and the characteristic in this case is the surface concentration Cs is fixed or keep constant during the diffusion process. This Cs does not change with time. Okay, so in order to get the concentration profile for case 3, in your textbook actually it introduced a Laplace transformation method to solve the concentration profile. So what's a Laplace transformation? If you apply the Laplace operator on the f function, then that means you okay, so Laplace transformation is transfer if the f is a function of x and t. So Laplace transformation actually is converted this f function from t domain to p domain, and we use the f hat to represent it after Laplace transformation. And how to deal with this? How to Laplace this function f? We just simply times the exponential minus pt and integral along dt from 0 to infinity. Then this is a definition to when we Laplace the function of f. So now we want to try to use this Laplace transformation to deal with the diffusion equation we are dealing with. So first of all, we need to Laplace the left-handed side and also Laplace the right-handed side. Then we solve the differentiation equation C hat in P domain and use some technique to convert this solution from back to T domain. Then you can get the solution C as a function of x and t. So this is a full picture like this. So first of all, you need to Laplace the left-handed side partial c partial t, right? So when you check the textbook, you can have some pictures on if we Laplace the f prime t, then you got the pf hat p minus f0. This 0 means the t equals to 0. So we just copy and use the same technique to deal with this partial c partial t, right? So we just replace the f as c. So p c hat minus c at t equals to 0. So it's like this. And the right-handed side is a diffusivity is constant, so we take the diffusivity out. And right-handed side, because this is a second deviation of c respective to x, right? But actually, this Laplace transformation is nothing related to x, so we just copy the second deviation here and just mark the after, because it's after Laplace transformation, use a c hat here. So now we just need to solve this diffusion equation to get the c hat. And in order to get the solution for this diffusion equation, you need to use a boundary condition. And here there are 3 boundary conditions. The first one is the at location 0 at any time point c equals to cs. So c equals to cs. This is the first boundary condition. And the second boundary condition is partial c partial x. The concentration do not change with location at positive infinity, which is far, far away from diffusion source. And at this region, the concentration do not change with location, so equals to 0. And the third boundary condition is at before diffusion, t equals to 0. Before diffusion, the concentration of diffusing atom at any location inside this material equals to 0. Okay, so in order to solve this diffusion equation, first of all, we use the third boundary condition. This term is equals to 0. So you only left this term and this term. So it will be like this, equals to 0. So this, you can get the solution. C hat, right, can be expressed like this in P domain. And we successfully get the solution C hat in P domain. But however, there are two unknown parameters, A1 and A2. As long as we get the A1 and A2, then you can get the complete solutions of C hat in P domain. But how to get the A1 and A2? We still have two unused boundary conditions, 1 and 2. So we have two boundary conditions, two unknown, A1 and A2. So definitely you can get the A1 and A2, right? Okay, so next slide, I just copy this here, and the unused boundary condition 1 and 2 here. So in order to get the A1 and A2, now we want to Laplace our boundary condition 1 and 2. So we Laplace the boundary condition 1 CS. That means Laplace this value CS, right? So it means you times the exponential minus pt and take the integral on t from 0 to infinity. Then you can get a CS over P. And if x equals to 0, and C hat will be this equals to 0, this equals to 0. So C hat will be equals to A1 plus A2. So I got this relationship from boundary condition 1. And if we want to, then next we Laplace transformation on boundary condition 2. This is 0, so times even you times this, you Laplace it, you still get 0. And at x equal x at infinity. So when x when x approach or at infinity, and this C hat, partial C hat, partial x will becomes to 0. That's only if you partial this with x at x equals to infinity, then becomes 0. The only possible is A1 is equals to 0. So because A1 equals to 0, so I got that A2 is CS over P. So only CS, this will drop this term out because A1 equals to 0. So solution of C hat is CS over P exponential term here. And you check the table. If you got the solution in P domain is expressed like this, then when you convert it back to T domain, can express like this. So if you check a look here, exponential term and P is at the bottom, it's quite similar, right? So we can successfully convert it back to T domain as what CS is, take it out. Then this time you can convert it to complementary error function. So if you not for you, and some people will convert it to complementary error function into 1 minus error function. So this is a solution for this case. And this case, if you take a look on the bottom line, the boundary condition 3, with boundary condition 3 here is before diffusion, the concentration of diffusing atom within this material is equals to 0. So the bottom line, is 0, right? That means this material does not contain the diffusing atoms before diffusion. But in order to explore the solutions used for more cases, so How about if your materials contain some amount of these diffusing atoms? So the third boundary condition should be changed from 0 to C0. So the corresponding solution need to modify by this, minus 0 plus C0. So you also can, after arrangement, you can get this converted complementary error function to error function. You can get these solutions. So this solution can be described, or is a solution for the constant service concentration cases. Okay. So the famous case for this constant service concentration cases or unlimited cases will be the carbonization. We have steel parts. We we continuously flow the methane and heat these systems up. Then the carbon atom is going to diffuse into this steel. And to strengthen the mechanical property of this steel, so we can measure, when you measure the concentration of diffusing carbons as a function of depth and time, then you can get these curves: 2 hours, 6 hours, 12, and 24 hours after diffusion. Then if you take a look at the same depth, you find that the concentration of the diffusion of the carbon increased over time. And in order to understand, in order to have more pictures or estimate the time needs to increase the carbon concentration to certain concentration at a specific depth, you need to use the solution you just derived from previous slide, right? So I give you an example. It's about carbonization, and what we have here is we want to carbonize a steel and at high temperature, and this steel have 0.18 weight percent of carbon. So the C0 is C0 is equals to 0.18 weight percent of carbon. Please calculate the necessary time to increase the carbon content from 0.18 to 0.35 weight percent at X equals to 0.4 millimeter below the surface of the steel. And we also assume the carbon content at the surface is CS is equals to 1.15 weight percent. And the diffusivity of carbon in gamma ion at this temperature can be expressed like this. So we just grab the equation, the solution we derived in previous case, and you can just put all the information in, and after simply calculate, you can get the error function. This value equals to 0.8247. When you check the table, you find that 0.8247 should be in between this error function, this error function, and so you need to use the interpolation technique. So just 0.8247 and use X. So you can just use this minus this one over this minus this one over this minus this one would be equals to this minus this one, right? This minus this one over this one minus this one equals to this one minus this one and over this one minus this one. So you get the X. So after calculation, it will take like 55.6 minutes. Okay, so next, so this is the example, so you can practice this. And next, related to diffusion length, usually we will use the square root of 40T to estimate the diffusion length in our experiments, in any experiments you are dealing with, right? But some people probably will ask, square root of 4dt, this diffusion length, is corresponding to what concentrations of diffusing atoms? What concentration of diffusing atoms compared to the diffusion source? So I listed the 3 cases we just discussed in previous slide and corresponding solutions. And if you try to plot in the square root 4dt, and you can have some pictures about at this location, what's the concentration related to associated with C0. So for this case, it's roughly, if you plug in square root of 4dt, is roughly the C0 over 8 at the C0 over 8. The concentration is roughly at C0 over 8. Why? You can have a look here. If the concentration becomes C0 over 8, that means this will be equals to 1 over 4, right? 1 over 4 means this error function will be 3 over 4. So the error function becomes 3 over 4, and this value will become, if you check the table, is around 0.8. So the x can become 1.6 square root dt, and it's roughly around square root of 4 dt. It's roughly. So at square root of 4 dt, is the concentration is around C0 over 8. And for the second case, if you use the square root of 4 dt here, then you find that at this the concentration will become what? This is CS, right? Before the diffusion, CS, we know the CS, right? Is times e to minus 1. What? Because you take the square root 4 dt here, so this becomes minus 1. So the concentration is like around like this. And for the third case, if you use the square root 4 dt here, and the concentration will be nearly like it will be equals to this. So this will become 3,4 will be equals to like this. If you just calculate, you use a 3,4 here, then you can get this concentration. And this will be the same like this, right? So x equals to square root 4 dt is roughly. So based on these results, you know that even although we use the square root of 4 dt to estimate the diffusion length in our experiments or in any cases we are talking about, but for different diffusion cases, diffusion patterns, the corresponding concentration of diffusing atoms respect to diffusion source before diffusion is quite different. For this one is C0 over A, and for this one is CS times E to minus 1, and this for third case is like this. And the other point of view is probably you, if you have no idea about what kind of cases happens in your experiments, then you can do one thing, right? You can simply get the square root of 40, the value for square root of 40t at this location or this depth. Then you can measure the concentration profile, a concentration at this location. Then you can check the concentration is more similar with which one, and you can say that, oh, my diffusion pattern is this one, belongs to this one, or this one, right? So this is the other approaches to if sometimes you confuse what kind of cases you can use for apply on your experiments, then you can do this kind of way to have some pictures. And by the way, for this case, if we assume C0 equals to 0, this is 0 and this is 0, so this will become CS over 4. This is 0, so this is, if this is 0 and this is CS, will be similar like this, right? Because CS does not change with time, and this point in diffusion couple also does not change with time, so this is CS over 4. CS over 4, and the CS here is 1/2 of C0, so it's quite similar, right? So for these two cases, have some this kind of relationship, right? It is one for this case, diffusion square root 40t C0 over 8 is roughly like at this region. And if you assume C0 equals to 0, like the C0 here is 0, right? And they have the same value for diffusion length, or same value of concentration of diffusing agent at diffusion length. Okay, so let's make a summary here. As long as you got the diffusion equation, you need to determine the boundary conditions belongs to steady state or non-steady state. Then you can get the corresponding concentration profile. And how to get this concentration profile? You use the step function, superposition technique, and Laplace transformation. Then you can get the solutions for each cases. Okay, so today let's end it here.